Good morning to all. This is Sivaya, Assistant Professor in the Department of ECE, Guru Nanak Institute of Technology. I will explain the step response of RC low pass circuit. So here I have taken the step signal as input. I am applying this signal to RC low pass circuit, and we have to observe the voltage across the capacitor. So here mathematically you can express this signal like this: Vi of t equal to V volts for t greater than 0. For t greater than 0, the voltage of this signal is V volts. It may be any value. You can take 1 volt, 2 volt, 3 volt or 4 volts. 0 for t less than 0. For t less than 0, the magnitude of this signal is 0. We are applying this signal to this RC low pass circuit. Next we have to observe the response of this circuit. Here I am observing the output across the capacitor. So here what is the function of capacitor? By applying the voltage V volts, it may be any value. For example, you can take 2 volts. So here current is flowing through the circuit in this loop. So here the capacitor stores the charge. Okay, the charge is accumulated across the capacitor exponentially. Here we know the relation between voltage and charge across the capacitor. C equal to Q by V, or you can take V equal to Q by C. C is constant. Here it stores the charge. The charge is rising across the capacitor exponentially, so the voltage also rising. Here if you see C is proportionality constant, you can take V proportional to Q. If the Q is rising, means it stores the charge, so the voltage also rising across the capacitor. If you observe the output waveform, this is the output waveform. So here the voltage across the capacitor is rising exponentially. So here how much time it is taking to reach the maximum value? The maximum value of the voltage across the capacitor is equal to the amplitude of the input signal. So it takes some time to reach the final value. Final value means that is the maximum amplitude of the input signal. This value V volts. It may be any value. For example, you can take 1 volt. If you take 1 volt, how much time the output is taking to reach the 1 volt value? So the voltage across capacitor is rising exponentially. So that depends on the R and C component values. Here that depends on time constant of the circuit. Time constant is R into C. RC is the time constant of the circuit. So this time, how much time it is taking to reach the final value, that depends on the R and C values. If you take the RC value small, within less time it will reach the final value. If you take the maximum RC, it takes the more time to reach the final value. So here, before going to see the output waveform of this circuit, we have to know the what is time constant and what is rise time. Rise time tau equal to 2.2 RC. Okay, mathematically you can derive this one after this theoretical explanation. So here the time taken by the output waveform to rise from 10% to 90% of its final value. Final value is, that is the amplitude of the input signal. So how much time it is taking? 10 to 90% of the value. For example, if you take this is 1 volt, so 10% of 1 is 10 by 100 into 1 volt or V volts. So you can get 0.1 volt. It is the 10% value, 0.1 volt. So if you take 90% of V, 90 by 100 into V equal to 0.9 V. So it is the 0.9 V. How much time it is taking to rise from 10% to 90% of its final value? Okay, this is the rise time. Okay, this is the rise time. So that depends on the RC value of the circuit, R and C components. So another parameter is time constant. Time constant equal to R into C. So here after some time it will reach the final value. What about the current in the circuit? So here we have to observe the three waveforms. One is input waveform, another one is output across the capacitor, that is this one. So next, current in the circuit. So at this instant, what about the current in the circuit we have to observe. For example, if you take input is 4 volts, input is this value, I have taken V. For example, V is 4 volts. So we have to see the what is the V0 value. V0 is the voltage across the capacitor. So we know the KVL, Kirchhoff's voltage law, by applying KVL to in this loop. So here applied voltage, input voltage equal to voltage drops, sum of the voltage drops in the circuit. So here you can take the voltage drop across R and the voltage drop across C. So here from the KVL you can write relation I equal to R VI of t equal to I of t into R plus V0 of t. It is the KVL. So applied voltage, input signal, voltage drop across the resistor and voltage across the capacitor. So for example, if you take 4 volts here, 4 volts, applied voltage is 4 volts. So initially there is no voltage across the capacitor. Capacitor charges exponentially, it takes some time to reach the final value, that is equal to amplitude of the input signal. So here initially, for example, if you apply the KVL to that one, voltage across resistor is 4 plus voltage across capacitor is 0. So it takes some time to reach the final value, it is rising exponentially. So at some instant, if you observe the values, 4 equal to, so here if you take this value is 3, voltage across resistor is 3, so the voltage across capacitor is V0 of t is 1. So here the voltage across capacitor is rising exponentially. So for example, at another instant, if the voltage across resistor is 2, the voltage across capacitor is 2. So at another instant, the voltage across resistor is 1, the voltage across capacitor is 3. At another instant, if the voltage across resistor is 0, the voltage across capacitor is 4. So when here if you see this one, this is the voltage across capacitor. So that is equal to input signal. After some time, it is reaching the final value. At this instant, output and input both are same. This is the input signal, this is the output signal. Both are same. If the see here 4 volts, output also 4 volts. At this instant, the voltage across resistor is I of t into R is 0. So here output across capacitor is 4, applied voltage is 4. Why the voltage across resistor is 0 here? So if you see the potential difference, here voltage across at this point, input voltage and output voltage both are same. So this, for example, this one is 4 volts, this one also 4 volts. So if you see, observe the potential difference, there is no potential difference, there is no current in the circuit. So current is 0 means current is 0, I of t into R. So that is 0. So all the voltage appeared across the capacitor. Suddenly if you remove the input signal, the voltage across capacitor is 4 volts now. So you can, now it acts as a battery. You can apply this voltage to next circuit also. We can operate the other circuit. So here if you see this waveform, the voltage across capacitor is rising exponentially. So at this instant, output voltage is equal to input voltage. What about the current at this point? At this point current is, input and output both are same, current is 0, then only voltage across resistor is 0. So at this instant, current is 0. So the voltage across capacitor is rising means the current is decreasing in the circuit. So it is the current waveform, current is decreasing in the circuit. At this instant, voltage across the capacitor is equal to input signal voltage. So at this point, this is the current waveform. At this point, current is 0. So here at this end, the voltages are same at this instant. Input is same, output also same after some time. Then current is 0. So if you see this one, current in the circuit is, so input voltage minus, if you take V of t, left side, V naught of t, this one is Vi of t minus V naught of t by R. So this is the current in the circuit. Input voltage minus output voltage by R. So here input is 4 volts, output is also 4 volts at this instant. 4 minus 4 is 0, 0 by anything is 0, so current is 0. So at this point the voltage is rising. So first I have taken 0, next 1, 2, 3, 4. After some time the output voltage is equal to input voltage. For example, I have taken 4 volts. So at this point the current in the circuit is 0. So finally you can say when the voltage across capacitor is equal to input signal voltage, the current is 0. Here at this instant the voltage is rising exponentially, the current is decreasing exponentially. So if you see here, this is constant, 4 minus 0 by R, maximum voltage we are getting. 4 minus 2, so reducing, next 4 minus 3, next 4 minus 4 by R. So current is decreasing. When the voltage is rising across the capacitor, the current is decreasing in this loop. So finally the current is 0 at this instant. So here if you see the time constant, what is time constant we have to know. The time taken by the output waveform to rise from 0 to 63.2% of its final value. Its final value. Its final value means, this is the final value means that is the amplitude of the input signal. So for example, if you take V volts, V is the amplitude of the input signal, 63.2% of V means 63.2 by 100 into V. So you will get 0.632 V. So see here, this is the maximum value is 1 volt, 0.63 V means this is the one value 0, 1. So half of this one is 0.5 volts, 63.2 means 0.63 is above 0.5. So this level is this one. The time taken by the output waveform to rise from 0 to 63.2. Okay, this time is tau, 0 to tau. So in this interval, the output waveform will reach the 63.2% of its final value. So here this one is exponential rising. So initially there is a linear rise. So if it maintains the linear rise, within this time it will reach the final value. Within this time it will reach the final value if it maintains the linear rise. Actually the voltage across capacitor is rising exponentially. So initially there is a linear rise, after some time there is an exponential rise. If it maintains the linear rise, so within this time it will reach the final value. Within time constant time it will reach the final value. Next we will see for different time constants what is the response of this circuit. So this level is input signal voltage level. So if you take 0.9 of this one is, this level is 0.9 level, this one is 0.5 level, this one is 0 level. So half of this one is I have taken, this one is 0.5 volts level. So here you can take 10% is 0.1 volt, 10% of V is 10 by 100 into V, so you will get 0.1 V. So V value maybe you can take any value. If you want to take 2 volts, you can take 2 volts. So if you take 2 volts, this one 0.1 into 2, 0.2 volts. So here this value is 0.2 volts. So actually I have taken 1 volt. So 10% of 1 is, we are getting 0.1 volt. So it may be any value. So here this is the input signal. If you observe the output waveform, output is rising exponentially. After some time it will reach the final value. So here what is the rise time? The time taken by the output waveform to rise from 10% to 90% of its final value. Final value is, that is the amplitude of the input signal. So here this time, this one is, I will indicate T1, 90% value is, see here 0.9 volt. To reach this level it has taken this much of time. So here rise time is tau equal to T2 minus T1. So this is the rise time. Time taken by the output waveform to rise from 10% to 90% of its final value. So it is the rise time. So based on the RC values, so for rise time, what is the equation for rise time? TR equal to 2.2 RC. If you take RC value is small, within less time it will reach the 90% of its final value. So based on the R and C component, so if you take maximum value, it takes the maximum time to reach the final value. If you take less time, R and C values are small, within less time it will reach the final value. So here for small RC value, so it takes less time to reach the final value. So if you see here, if you take small RC, within less time, in this interval only, it will reach the final value. If you increase RC, it takes more time. See here this waveform, it has taken more time compared to this one. To reach 90%, it has taken only this much of time, but to reach this waveform to this level, it has taken more time. Okay, that depends on the R and C values. If RC time constant is small, within less time it will reach the final value. So if you take very small, in that case, see here to reach the final value output waveform, it has taken only this much of time only. For small RC value, if you increase RC, you will get like this. If you take again, if you increase, it takes this much of time to reach the 90% of the maximum value. So if you see here, for small RC values, there is a small deviation between the input and output. So it is for small RC, okay, it is the output waveform. See here, if you observe this waveform and this one, there is a small deviation. If you see this one, if you take maximum RC value, there is a maximum deviation compared to input signal. Okay, like that, if you increase the RC value, suppose if you take large value, it may take more time to reach the final value. For large RC value, the waveform is like this. Again, if you increase, so it may take more time to reach the final value. That is the amplitude of the input signal. For large RC, see here, if you observe this one and input signal, there is a maximum deviation. So it has taken more time to reach the 90% value. See here, this is the 0.9 volts, this level. To reach this level, it has taken more time. Okay, if your RC value is more, takes the more time to reach the final value.